Hello and welcome to the next open learning session where I'm going to catch up with deep learning. I'm working with this book called Mathematics of Machine Learning. It's an open MIT book and the link is in the description. And today we are tackling the chapter regarding the Gaussian elimination. It is in 2.3. I think it is called the minus trick, the minus one trick. In the following, we introduce a practical trick for reading out the solutions x of a homogeneous system of linear equation. Okay, so we have a matrix A, and then we're looking for a solution x, or a set of solutions, right? To start, we assume that A is in reduced row echelon form without any rows that just without any rows that just contain 0. There's not a single row which only has 0. There's always a 1. And we are having something like some kind of a staircase form. So the asterisk can be any arbitrary real number. And we always have a pivot number in the beginning, which has to be 1. Okay, so this one means everything else 0. Everything else on this column except this one pivot number. The columns J1 to K with the pivots marked bold are the standard unit vectors E1 to K. All right, so I know that if we have something like this, where only we have 1 and only zeros, this is like a unit vector. Also, if I remember correctly, this is like a new base system. It's like when you have one base system and then you translate it all into another base system. Basically, every vector can be also be expressed as a linear combination of the second base system. We extend this matrix to an n times n matrix by adding n minus k rows of this form, which means it has only zeros except 1 minus 1, and I guess the position of this 1 depends, so that we have this dialog thing keep going, and we call this new matrix a hat. Okay, so we start with an a k times n, and what we actually want is an n times n. So we make it we make the matrix taller. We might have something like this, and then we have something like that. So we make it taller. Yeah, so it has to be a square. The columns of a hat that contains the -1 as pivots are solutions of the homogeneous equation system AX equals 0. Okay, so the columns. I'm not sure if I understand this correctly. So we have these columns. So let's say this is a column where it has a -1, a -1 in the pivot. And this one has to be a solution to the equation AX equals 0. So it is AX, not a hat. To be more precise, these columns form a basis of the solution space of AX equals 0, which we will later call the kernel or null space. All right. we have something new, a kernel. So I guess the kernel is the columns which form a basis. Okay, good. Next point, example 2.3, 2.8. Let us revisit the matrix 2.49, which we already had in reduced echelon form. Yes, we have that matrix which is 3 times 5. And we want to shift it into a 5 times 5 matrix. We are adding 2 new columns. Yes, and the position of the columns are obvious because we know that we want the pivots all to be in a diagonal. So the first one has to be on the second row and the last one is in the last row because these are the ones which are missing. So we have this diagonal. Okay, now they're saying we can immediately read out a solution. Okay, so they are saying the solution is exactly, the first one is this one, and the second one is that one, because of the -1 in the green line. Okay, this should be identical to what we had before. Let's double check that. It's 3, 1. Yes, I can remember. It's the same. Yeah. 3, 1, and the other one is 3, 0, 9, 4, 1. Yeah, okay. Interesting. But I guess it is the same thing as what we did by just reading out the columns, right? And putting a 0 where we had 2 variables. Okay, but this is quite a nice trick. So what do we have now? Calculating the inverse. To compute the inverse, A inverse, let's call it, we need to find a matrix X. In this case, X is a matrix. That satisfies, yeah, we do a matrix multiplication and get the identity matrix, which is just a bunch of zeros in the diagonal. Okay, so in that case, we know that this matrix X is our inverse. We can write this down as a set of simultaneous linear equations. A times X equals identity, where we solve for X. Okay, they want to write it as an augmented matrix notation. Usually we have a constant, right, on the right side. So when we have something like this, yes. So we have the coefficients on the left side, and then we have the constants on the right side. And the coefficients are, it's a matrix, it's a block of numbers, and the constants are just, they're just a vector. Let me double check what we had before. Yes, that's exactly what we had before. All right, so what they're doing is they want to write the coefficient, I'm sorry, they want to write the constant like in a identity matrix form. Okay, here's my problem currently. The identity matrix is a block, is two-dimensional, and I'm looking for a one-dimensional thing. Maybe it does not really matter. Okay, I don't know. Let's just move on and let's see what's happening. This means that if we bring the augmented equation system into reduced row echelon form, we can read out the inverse on the right hand side of the equation system. Hence, determining the inverse of a matrix is equivalent of solving systems of equations. I'm not getting it. Okay, let's check this example. We have a 4 times 4 matrix. It's already Yeah, it's already a square matrix, but it is not in reduced echelon form. So what they do is they first augment it. So this part should be here, and here we have our identity matrix. Are we trying to just manipulate these numbers so that we shift that one, so that we shift this one here to the left? I don't know. Okay, again, what they're saying is they want to have a system of linear equations. And this line can be dividing not only a vector with a matrix, but also two matrices. So I don't know, in my head it was always a vector. What they're saying is, okay, you have like this system of linear equations, and we are looking for x. So this one, this should be x, right? Because we have here x is our inverse and can only be satisfied if x also, if you multiply a with x, you will get an identity matrix. Now I'm not getting why this is true here. Like, I'm understanding that if you have a matrix A and you multiply it with the matrix X and you get an identity matrix, that X has to be the inverse. Okay, that's quite easy to understand. And what they're doing is they say we can write this down as a set of simultaneous linear equations. Okay, let's go back to how this actually works. We have a equation usually like this: matrix times vector equals b, a new vector. Now they're saying we have matrix times matrix X equals identity matrix. So that's why we have now our system of linear equations, something like that. And if we remember how multiplication works in, okay, let me shift to how multiplication works. We have something like this, right? So a 3 times 2 and a 2 times 3 equals a 3 times 3. So basically the first dimension and the last dimension in the chain. Yeah, this one is the first, this one is the last. And what we are doing is we're taking always that one, and this one becomes that number. So it is always a vector multiplication. It is a scalar product. And in the end, we have 9 different scalar products. Basically every multiplication possible. Okay, so that means now, okay, I'm not getting this part here. Not getting this part. So we have the matrix X, which is basically our unknowns, but they divide it in different columns. Like if this whole thing would be just the first column here, then that would be easy. But I don't know if this can just be translated, because here we have a set of linear equations. I'm not sure. I really don't know. I think what we can try is to solve this problem and see if we get actually the same answer. Okay, so let's just write down the number. This will take a while now. Okay, the first thing I'm doing is I say minus row 1 here, and here, and here. Okay, so we will have a 0 here, then we will have this 1 here, minus 2, 0. Here we have the minus 1, 1, 0, 0. So third row will be 0, 2, -2, 1, -1, 0, 1, 0. Okay, let me double check this one. Okay, then the last one will be 0, 1, -1, 1, -1, 0, 0. Here we want to take the second row 2 times to get rid of the 2. And here we can actually, yeah, we can subtract 2 times the third row. Okay, so row 3. Okay, again, how does that work? We will have a 0 here anyway. We will have a 0 here. Then we will have a 2 here, and 1 remains. Here we will have a 1, a -2, a 1, and a 0. Okay, the last row will be here we will have a 0. Yeah, that's wrong. We cannot have -2 R2. It has to be a half, right? So then we will have here 0 as well, and 0 here, a half here, another half there, minus a half, 0, minus a half, and 1. Okay, so the next step would be to just get rid of the halves here. I will scale this up. So we will have here 1, -1, 0, -1, and 2. Okay, so the next step would be to remove here the the 1 on this row. I think -R4 what we need, right? And afterwards I would just scale it down. So we can do 2 operations, right? I think this should be no problem. Okay, so the first 2 zeros will be untouched. Then this one will be 1. Here we will have 0. And the next one we will have 1. Then we will have here -1. This should be 1, 2. Okay, so wait. 1 plus 1 is 2, divided by 1/2 is 1, right? And the last one will be -2 and then -1. Okay. Okay, good. And what we need to do here is basically we need to subtract -R3 2 times. And here we have to add 2 times R3. Okay, so first row. The first one will be a 1. And the second one will be a 0. Here we will have a 0, 2. And here we have a 0, 2. So more complicated is the right side. We will have here -1. Here we have a 2. Then we have a -2. And then we have a 2 again. So the second row, 0 is 0. Here we have a 1. Then we add just 2 times the 1 there. We will have a 0. And here we have a 0, 2. Okay, so this will be a 1, a -1, a 2, and a -2. Okay, I hope this is right. Do we have the right numbers? -1, 2, -2, 2, 1, -1, 2, -2, 1, -1, 1, -1, -1, 0, -1, 2. Whew. Actually, I'm quite surprised it worked. So I have not fully understood why this actually works, but I can calculate it. Like this is enough to actually pass the math exam, but it's not enough to actually make deep learning work. So this annoys me a bit, but it's hard to get intuition just by forcing yourself. I feel like I'm going to work more on the problems and then watch. At some point, we will watch a few videos um, where other people are explaining stuff, and then maybe we can connect the dots. Okay, so let's move back to the textbook. Yeah, so here we actually made the calculation. It's also the end of the chapter, I guess. Uh, is there anything I can add? Not much to add. All right, I will make a cut here and then we will see each other in the next video. Thank you.